what you need, and what you find difficult, no problem. But we must be very clear about many aspects before we can proceed and kind of go through this course. So now the item number 6 here in my plan is very important. So let's make some notes, please, as we go along. So the idea of moment of a force. So a force can have translational effect, which is a linear movement, but a force also can have rotational effect, as you can see here from the idea of the door. So if you have a door, like I'm sure you open doors every day and so on, and then you apply a force at the edge of the door as a knob here, the handle, to open the door. Because when you apply a force here, it has a rotational effect, which results in opening the door. And interestingly enough, you have the handle of the door at the edge of the door, not in the middle of the door. And there is a reason for that, because if you have the handle here, the force will have higher value of rotational effect than if you have the handle here. But the idea of rotational effect is clear. So when this happens, when an applied force results in a rotation or tendency of rotation around a point or in the plane of the forces, the force then is said to exert moment M about this point. To exert moment, rotational effect. So the moment is a rotational effect of the force. if we're talking about two-dimensional or 3D, the force will cause a kind of rotational effect or tendency of rotation. All right. So if we're looking at a force F here in the plane, now we're talking about 2D for now. And if you have any point in the plane of this force, or it can be 3D, but for now we're just talking about 2D. So the rotational effect of this force about this point here, so the rotational effect of M, so the rotational effect M of the force F about O is, have a look, of course, it is F times D, F times D. But what you must appreciate this, the D value, the distance must be the perpendicular distance. So M is equal to F times D. F is the force, D is the distance between the line of action of the force and the point, but it is the line of action, this distance here must be the perpendicular distance from the point to the line of action of the force. So if you want to calculate the rotational effect of F about O, you must find this precise distance D, which is the perpendicular distance between point O and F. Okay? So the value D is called arm of the moment. Arm, like your arm of the moment. So it's always good to talk about what is the arm of this moment? What is the arm of this rotational effect of this force? So someone already did the example and was a vector kind of formulation. So thank you very much. So you obviously know quite a lot about that. Wonderful. It looks good as well. So thank you very much. And that is 10. So thank you very much. I'll keep a record of your name. Sorry about the interruption, but we will proceed. I will just write the name of 10 who did this, the example I've just mentioned. So please advise me if the information I'm presenting to you now is basic and you don't need it, so I can move on. If you're all confident with this, or I can move quickly maybe. So if you have the point O here, and the force, the line of action of the force here, so the moment of this force about O. Thank you very much. And I have another solution here of example 6. Fung. Again, I will keep a record of the names later on, but that's wonderful. That's great. So you seem to be good. You seem to have quite a lot of knowledge about this, some of you. So I hope all of you the same. So again, the moment or the rotational effect about O is F times D, and D is a perpendicular distance. Please advise me if I need to move quickly about this topic, if it's easy for you. So perhaps now you can write this very quickly. What is the rotational effect? What is the moment value of this force about O? Is the force times the perpendicular distance, which is easy, very easy. So M equals force times arm of the force. How about this one here? Maybe someone can tell me very quickly, what is the moment of this force about point O, please? Very basic information. 50 times what gives me the moment, the rotational effect of this force about this point? How much? So yeah, so please appreciate that the moment value is the force times the perpendicular distance. The arm must be here, okay? I've got here 100, but please appreciate in the chat box, yeah, said 100 kilonewtons. Have a look, please. You are multiplying a kilonewton by a meter. So it's not kilonewton. Kilonewton is just for the force, but the units of the moment, thank you very much, the unit of the moment is kilonewton times meter. Excellent, yeah, excellent. There is a correction. I will keep a record of the chat box later on for your engagement. That's wonderful. So in addition to this, so here it is, please note. So the first one is 50 times 4. 4 is a perpendicular distance. And here is, this was a problem with a unit, kilonewton times meter. So please appreciate that the units are kilonewton meter. Some textbooks put a dot here between the kilonewton and the meter, but it's okay for me if you write it as kilonewton meter or kilonewton dot meter, it's okay. And have a look, please. The rotational effect has got a sense. So if you imagine this is a two-dimensional plane and there's a force acting in this plane, so the entire plane now is rotating in the anti-clockwise or counterclockwise or anti-clockwise, the American pronunciation anti, the British pronunciation anti-clockwise or counterclockwise, all the same thing, going in the opposite direction to the clock. So this is a sense. So you have a look, please. Moment has got a value, a unit, and a sense or direction. And if anyone is missing, is not correct. So it must be, all this information must be clear when you provide your answer. So thank you very much for everyone who did on this example here. And here it is. So again, we are talking about the moment of this force about a specific point O. So it's F times D. F is clear. D is not clear. It is 4 sine 30 degrees, which is half the 4, of course. And you have 100 kilonewton meters in the counterclockwise direction. So sometimes we want to really do a lot of calculations. So we don't want to say, oh, anti-clockwise or counterclockwise, clockwise. So we have an agreement. And here is the agreement. So the word agreement is sign convention. Of course, you don't see pluses and minuses in the building where you are or in the bridge where you travel or whatever. So we agree, as engineers, we agree. But physically, we need to appreciate the physical meaning. So you can use this agreement or this agreement. It's up to you. Some textbooks like this agreement, which is fine, and I understand why. Or I can, sometimes they use this agreement, which is okay. So either agreement should provide the same answer. It's just an agreement. So the word positive is abbreviated in English anyway as a plus VE, and the word negative is abbreviated minus VE, but that's not important. So this is a positive direction, and this is a negative direction, or the other way around. But you need to keep the convention. So you can either use this one or this one in one, at least in one problem. So if you are solving one problem, you can adopt either of them according to what you like. But you don't mix, of course. If you mix, you will have the wrong answer. So this is what we call sign convention or sign agreement. Okay. Another very important information for you is if you consider the rotational effect of any force along any point along the line of action of this force, it will be 0. So moment about points on the line of action of a force must be 0. So a force does not produce any rotational effects around any point on the line of action of the force. So moment of F about any point O along the line of action of the force is 0. And that is very useful when we calculate reactions later on. All right? Very soon I'll give you some examples to work on. Couples, very important in engineering. The idea of couples, really, really important. So if you consider two equal and opposite forces parallel to each other, and we are going to find the moments or the rotational effect of these forces around point O. So let's have a look here. So these two forces, F and F, are equal and opposite directions and parallel to each other and having a distance d between them. Perpendicular distance between the two forces is d. Okay, and we can adopt this sign convention for now. As I said, it's up to you, but this is my agreement with you. And let's find out the rotational effect or the moment of this system about any point O in the plane of these two forces equal, opposite, and parallel to each other. In 2D, in a plane, if you like, how much rotational effect they will produce in this plane where they are acting. And it doesn't matter really where this point is. It can be very far, it can be even up to infinity. It does not matter. This will be valid. It does not matter. So the moment of this force system around point O is this F going in the positive agreed direction about this point, trying to rotate the entire plane in the clockwise direction. And the distance or the arm of the force is OA, okay? And the rotational effect of this force about the same point is trying to rotate the entire plane in the counterclockwise direction, in the negative direction, and the arm of this force around O is OB. So basically the situation is the total rotational effect of these two forces, equal and opposite and parallel, around any point in the plane of the forces up to infinity, is this F times D, F times D, acting in the positive direction. You can see F and D acting in this direction, trying to rotate the entire plane in the clockwise direction. If you reverse the forces, they will try to rotate the entire plane in the counterclockwise direction. So this couple actually acts in the plane of the coplanar couple and trying to rotate the entire plane, and the rotational effect is F times D. D is a perpendicular distance between the two forces. Very important when you progress with your courses, even in design, when you carry out design of cross sections of bridges, amazing composite systems, and so on. There are lots and lots of couples happening inside the material as well, because your course is about strengths of materials. So it's about stresses inside the material and so on. And you will see these couples inside the material acting between the grains of the material later on. But for now, we need to appreciate that. So again, the units will be whatever units you're using, kilonewton meters, and the direction you indicate the sense, the effect of this couple in the plane of the forces. So here it is, please appreciate that. The system of two equal opposite forces is called a couple. A couple, usually it means two people in love, perhaps, or partners or whatever. But here it's two forces equal and opposite and parallel to each other, and the perpendicular distance is d. And this couple, the moment of this couple at any point in their plane is F times d, and the sense according to the direction of the couple, whether it is clockwise or counterclockwise. In this case, it is actually in the clockwise direction according to the sign convention, and you can proceed with that. Okay, so I'll give you some examples to make sure you understood this little idea, and I'm sure you will do very well as a quick revision, but please advise me as if this is too easy, and if it's too easy, I have a lot of material to cover with you. So let's have an example, please. So here's a very easy example, and you can do it very quickly. You can shout even, you can switch your mic on and tell me what is the moment or the rotational effect of this force about this point here. Straight away, wonderful. But please remember the units and the sense. I can see many answers in the chat box and you forgot. Yes, exactly. So that is really what I'm looking for. Thank you very much. Again, I can see also many people. Wonderful. I'll keep a record of all of that. All of you are engaging in the chat box. Wonderful. But please remember the units. Yeah, so the units and the sense. Because as I said to you, if you just say 200, it doesn't mean anything in mechanics. Exactly, 200 Newton meter in the clockwise direction, which we agreed for now to be the positive direction. So if you have an element like this, and this element is supported here, so this force will try to rotate this element around this point, and the amount of the rotational effect, the amount of moment is the force times the arm, and the arm is the perpendicular distance from point O to the force, and the value of the rotational effect is 200 Newton meter, and the rotational sense is in the clockwise direction. Wonderful, great, great, great. Okay, all of you are confident with this. Physics, but very important. Again, here, as I said, some textbooks and some engineers like to pose a dot. It's okay for me if you don't pose a dot, it's fine as a quick way of writing. That's also fine from my point of view. And you must indicate the sense here, indicating still with the arrow, which I actually prefer. But of course, in the chat box, you can indicate with a sign. But I actually prefer this arrow here to tell me what's happening. And I also like to mention the convention before I start solving the problem. I say this is my positive direction or this is my negative direction. Another one, please, quick. Again, shout in the chat box, and I will see the chat box in front of me. So what is the rotational effect of the force 50 Newton? Again, around point O. So this is all in one plane, two-dimensional, and you have, for now, you can think about the component here, but actually it does not matter for now. We're talking just about the force and a point in the plane of the force and the rotational effect for the entire plane, actually. So the rotational effect acts for the entire plane. But we're trying to establish the rotational effect of this force around this point, please. Any answers? So I'm watching the chat box. Wonderful. Now many different answers. Some are mostly good. Yeah, thank you very much. Yeah. Good. I am very happy to see you all engaging and writing the answers on the screen. Again, please remember the sign and the units and all of this, but it's okay. So basically what we have here, please remember the idea of force times distance, and a wonderful, great, correct answer. And you need to establish the extension of this force. I think only maybe one answer wasn't accurate, but mostly all the answers were accurate. The point is here, the line of the action, the extension of the line of the action of the force here, 50 times 0.75 meters, and the rotational effect, as you can see here, is force times the arm of the force around this point. The arm is here, and it is 37.5 Newton meters. Doesn't mean anything without that. And the rotational effect is in the clockwise direction, which we said we will take it as positive or whatever, but here it is indicated with arrow indicating the sense of the force. Wonderful. Okay, you're all very good. How about this one? Quick again, shout the answer in the chat box. Sorry, not complete sketch here. So what is rotational effect? Again, later, because we are talking about material and strength of material, later we are going to investigate what is going on inside the material. But without appreciating these ideas of moments and so on, again, here we have various answers here, actually. Okay, okay, yeah, good. Wonderful. Again, please, yeah, okay. So you can put the sign in front of the number, or you can tell us or you can give us the arrow indication, indicating the direction of the moment. But wonderful. Again, we have the extension of the forces here. So it doesn't really matter. What matters is the arm of this force around this point, the moment arm, which is basically this perpendicular distance here, which is 4 minus 1, which is 3, 7 times 3, 21 kilonewton times meter, kilonewton meter, and the sense of the moment is in the counterclockwise direction, which we agreed to be the negative direction. But according to our agreement, whatever the agreement might be. So again, I know maybe it's for you it's better in the chat box to write minuses, but it will be good in the future to use kind of the indication as well. So if it comes out as a minus, you can indicate the wonderful. I'll keep a record of all the answers in the chat box, but many of you now are engaging, which I love to see. Excellent, thank you very much. Okay, so that's very basic. All right. So let's go on and increase the difficulty a little bit. How about this one, please? Again, that you might need a bit more time. So go ahead, please, and try this problem. So I think you are finding this easy, which is okay, which is good, but try, let's see what will happen here. Things might now become a little bit confusing, but not much really. But this is the kind of thing we are interested for you to be able to do confidently and quickly. And this will stay with you throughout your program of studies. So again, we have the x and y, and we have the point here, but the x and y just reference axes, orthogonal, perpendicular to each other. You know, in engineering, usually x is the horizontal, y is the vertical. But yeah, and we have these forces, and I'll give you a few minutes to give me the resultant moment of all these four forces acting on this rod about this point here. This point here is significant in engineering, but it can be any point in the plane of the forces. So I will wait for you to give me the answer. So again, you have to start with the agreement which direction of moment is positive. And of course, here some forces will have clockwise rotational effect around O, and some forces will have counterclockwise rotational effect about O, and some forces will have zero effect, a rotational effect around O. Great. We have many solutions provided in the chat box. Wonderful. So we are confident with that. So have you done this before in the physics course, perhaps? Or you understood quickly? But we will have a look and check your answers together. If you're ready, before we have a break. So yes, most few got the answer correctly, which is wonderful. Thank you very much. Excellent. Again, I will copy the entire chat box later and keep it in our records for engagement. So that is wonderful. So yeah, great. So you can use positive or negative, or you can use this idea here. Up to you, really. So before we carry out the calculation, we indicate which direction is positive. In this solution, it has been opposite to what I used earlier, but it doesn't make any difference. Finally, we will have the correct answer and the correct sense of the moment, which is in the clockwise direction. So if your solution was positive, it is correct because you have indicated the positive direction as a clockwise direction. So basically the final answer is 334 Newton meters in the clockwise direction. Clockwise direction. Okay, so in your case, if you assume the different sign convention, these signs will be opposite, and and then you will have the correct answer anyway. So that is really the correct answer is 334 Newton meter in the clockwise direction. So if you look back here, just make a note, please, that when you have a force going through the point, you have zero rotational effect of this force around point O. 50 will have a clockwise rotational effect around O. 40 will have a clockwise rotational effect about O, and the 20 will have a counterclockwise rotational effect around O. So thank you very much for your efforts, and I'm very happy because you're engaging so well. So I'll leave you alone now to have a 10 minutes break, and we will come back and we'll continue. Maybe we'll go a bit faster later on today to achieve more, but you are doing very well. Okay, so I'll leave you alone now, 10 minutes. We'll come back at 10 o'clock. Thank you. Thanks. Okay, hello again. So we'll start again. Yeah. Great. Thank you. So, so this is a little kind of practical example about the moment, and you will encounter the idea of moment in engineering and structures and buildings, bridges, skyscrapers, towers, everywhere. But here is a simplistic example. This tool to remove the nails. There is a nail here, and this tool here is used to remove the nail out. So this tool is resting at this point, and then you're pulling it here, and the nail is resisting here. And of course, the arm here is causing rotational effect this way, about this point, and the nail is resisting in this way, but your effect on the nail, your effect, rotational effect about this point must be greater than the resistance of the nail in the opposite direction to be able to lift the nail up. So very kind of simple, practical examples you can think about. You can watch what's happening in reality and think about the rotational effects of the forces. Okay, very quickly again, I hope this is useful. So we're talking about 2D. We're talking about rotational effect of the force F about any point O. So this is the M about O of the force F. And the line of action, the extension, of course, the line of action of the force go to infinity, both directions. But here we are looking at the extension of F and the perpendicular direction to point O, and of course F times D will give you the moment of F around point O. We've done this, that's all the information. But the idea, the principle of moments, that so the moment of this force about point O is equal to the sum of the moments of the components of this force around the same point. So the moment of F about O is equal to the sum of the moments of the component of F in the x direction plus the moment of the component of F in the y direction around the same point. And of course, you have the rotational effect of Fx is Fx times y acting in the clockwise direction, and the rotational effect of Fy is Fy times x acting in the counterclockwise direction around the same point O. So you have to be wise and realize that the rotational effect of a force is equal to the sum of the rotational effects of the components of this force around the same point in the plane of the forces. Here it is. So I think again in this text box, the negative has been taken as the counterclockwise direction from Fy, but as I said, it does not matter really, as long as you follow the same convection, the same agreement, and Fx is going in the clockwise direction here, which is positive, taken as positive. So, so that is really the situation here. Okay, so the moment of the force around point O is equivalent to the sum of the moments of the components around the same point. And here you go. Can you do this for me, please? Again, this can be done very quickly, and it can be done by the force times D, or by the components in a x and y direction. and you can actually choose the x and y directions in any directions you like. So the x doesn't have to be the horizontal and the y doesn't have to be the vertical. So I'll leave you to do this quickly for me, to just highlight this idea of the principle of moments. So the moment of force F around point O, please. So I'm watching the chat box, so I expect you all to do it quickly. Great, we have here some answers. And by the way, you do not need to convert the kilonewtons to newtons. You can leave it as kilonewton times meter. That is okay. So again, wonderful. A number of students already found the answer, and it seems to be agreement in relation to the answer, which is easy. So you can do it like this in an easy way. You calculate D, and it is going in the clockwise direction, 14.5. Again, you need to indicate the positive direction. If you like, you have to say which direction is positive, which direction is negative. So it's okay for you to say now it is positive, but in the future you can, when you do this in the exam, you have to show us, your assumption, what is positive and what is negative. Wonderful. So that is solution number one, which is great. But you will get the same solution if you do this, and maybe I'd like you to try it as well. So now you can establish two directions, orthogonal directions, x and y. And you have here the origin at point O. And you can resolve the force F in the x direction and in the y direction. So again, this is a resolution of forces, which I highlighted at the start of the session. So this F here, you can replace it by Fx, and you can replace it by Fy components, two components. And of course, you can calculate the distances, the arm of Fy, which is dx, 3 cosine 30, 30 is here. And the arm of, this is the arm of Fy, and this is the arm of Fx, which is dy. And again, you can calculate the arms very easily, the perpendicular distance from the components to the point, or from the point to the component of the components of the force. And again, please, you will get the same answer. So you can try it, and you will get the same answer. So Fy times dx acting in the clockwise direction plus fx times dy acting also in the clockwise direction, and this will give you exactly the same answer. So here in this solution, the textbook decided to use the counterclockwise direction as positive, which is, I understand why, there is a reason for that, but it does not matter for us as long as we arrive at the same conclusion that the resultant moment is acting in the clockwise direction around point O. So that is really a straightforward kind of idea. Okay, and there's another way, another solution, and here is the other solution, which also a clever solution because you can solve the force, resolve the force in two directions, perpendicular to each other, x and y, and the x actually is along the axis of this rod. You are free, you have total freedom. And then you can resolve the force into two components. One component along the axis of the rod, which goes through point O, and one component perpendicular to the axis of the rod. And again, you can use the resolution of forces idea with the geometry. So the force times cosine 75 will give you the component along the x, and the force times sine 75 will give you the component perpendicular to the axis along the y. And then you, in this case, the rotational effect will be just the Fy component times 3, because the x component is going through the point here, which produces no moment around point O. So many ways you can do the same thing, but the final answer is exactly the same. Again, in this textbook, where this example is taken from, they decided to have an agreement that the counterclockwise direction is positive, but the final answer is exactly the same like what you have done before. So this is just to show you different ways of solving the same problem. It depends on what you need to achieve in the problem. And later on, we're going to look at what's happening inside the material when you have these forces and axial forces. So if you're just interested in the axial effect on this element, you are more interested in this component of the force acting along the axis, and so on. So there are many ways you can actually look at it, and you can apply your ideas. And all of them, as long as you have the final answer, you find the correct answer, all of these ideas will be accepted. Okay, so that is really what is happening here. So the other idea, which I suspect you have already done before, and maybe we don't need to do it in detail, is equilibrium of concurrent forces. I think you've done this before, perhaps in physics or some basic mechanics. So static equilibrium of a particle. So now we're talking about a particle, which means at forces acting on a particle, meaning forces acting at a single point, because you can think about a particle really as having no size. There is no size to it. So the idea of forces, coplanar, concurrent, meaning forces acting in one plane and meeting at a single point. And they have reference axes x and y. So basically, for static equilibrium, the sum of the components in the x direction must be equal to 0. So you have many forces, if 1, 2, 3, 4 acting in one plane, coplanar, and acting on a particle or meeting at a single point, which will be very relevant to truss systems when we analyze truss systems later on, perhaps next week. So the sum of these forces, the sum of the components in the x direction must be equal to 0. And I like to write it in a simplistic way. Components going to the left, the sum of the components going to the left must be equal to the sum of the components going to the right. Very simple idea, but the mathematical idea, of course, is this: sigma fx is equal to 0. Vertical equilibrium, in fact, equilibrium in any direction, equilibrium in any direction. Again, the sum of the components in the y direction must add up to 0. So again, in a simplistic way, in an easy way, I also look and make sure this is the case, not just writing the numbers. I look and say, oh yeah, some forces going up and some forces going down, and the sum of the forces going up must be equal to the sum of the forces coming down. Or mathematically, the sum of the components going up plus the sum of the components going down, or the sum of the total components using pluses and minuses, the sum of the total, all the components must be equal to 0. So this is a very basic idea, but really very important, as you will see when we analyze trusses. So there are many examples, and I think you can find a lot of examples in the textbooks. But perhaps what the other idea, which is very important for us, and I will give you just kind of homework to do, a little bit of homework to do later, but for now, there is another idea related to equilibrium, static equilibrium of coplanar two-dimensional forces, but they are non-concurrent forces, which means these forces do not meet at a single point. So again, we're talking about 2D. For now, I think you can expand on to 3D very easily once you understand the ideas of two-dimensional kind of analysis first, and you're comfortable with that, we can expand. So these are non-concurrent. They don't meet at a single point. In this case, you have 3 equations of static equilibrium. 2 of them are related to translation of this plane, translation, movement, linear movement. Linear movement in any direction, actually, but now we're just thinking about reference directions, x and y. Linear translation, there is no linear translation of the system. 2 of them about translational effect of the forces, all the forces. And 1 equation is related to the rotational effect of the forces in the plane of the forces. Rotational effect. So if the force system is in a static equilibrium, the non-concurrent force system in a static equilibrium, there are no translational effects and no rotational effects. I will have to say something a bit more, or sometimes you can think about, but this is more like dynamics, perhaps not for us in civil engineering as such, or moving with a constant velocity in relation to these effects. There is no acceleration. But for now, to kind of not complicate your life, for static equilibrium, sigma fx, the component of forces in the x direction are equal to 0. The sum of the components of the forces in the y direction is equal to 0. And the sum of the rotational effects of all the forces around any point in the plane of the forces in all directions up to infinity in all directions, the sum of the rotational effects, the sum of the moments of all the forces about any point in the plane of the forces must add up to 0 for static equilibrium. And I think you've done this already for me, so I'm not going to go again over it. And I think many of you did it correctly. But we can move on. I believe this has been done before. Please confirm. We have done this before. So here, if I'm saying there is a force F1 and F2 and F3 are not known, and you have this body, rigid body, solid body, it can be anything. And in fact, it can be just forces in one plane without thinking too much about the rigid body, if you like. And you have 10 kilonewton and 10 kilonewton acting in this plane, and F1 and F2 and F3. And if this system is in static equilibrium, you can apply 3 equations to find the 3 unknowns. And I think you've done this for me before. So maybe we'll move on and look at applying the same thing, but maybe for reactions. If that's all right. Okay. So let's have a look at maybe one more example. So I think we can leave this topic and look at another topic related to support reactions, if that's all right. So now we are going to move on. If you don't have any questions, we are going to move on and start a topic related to support reactions. Is that okay, Professor Ben? We do that now? Yeah? Okay. So another area which we need to be clear about before we move on is related to loads and reactions. So the requirements from here is for you to appreciate the nature of supports and to calculate the support reactions using static equilibrium equations, which I've just mentioned very quickly, but now we're going to apply them in detail. So I think maybe I've given you this information before. So there are some ideas about loading on the structure, which I don't mind. I can show you this presentation quickly, not in detail, just to highlight to you what is coming. I'm not going to go through this presentation for a long time, but just for you to appreciate the ideas, what we are trying to achieve. So this is a small presentation here, which you can see in front of you. And it's about structures. I cannot see you now, I'm afraid, because I have the same screen in front of me. So we have building systems, and you have all kind of loading acting on them. So in another time, I will go through this in detail, but you have static loadings, and you have dead load, and you have live load, and in Europe and everywhere, we have to think about variety of loading, about self-weight, and about live load and vehicles, and in Europe about snow and all of that, wind, waves, earth pressure, settlement. So you will encounter loading in many situations, and you have to be aware of the type of the load applied on the structure to be able to analyze it. And there is a lot of guidance from the code of practice about all these different types of loading effects. I'm going through it in quickly, just put some images in front of you for you to appreciate what we are going to be looking at in the total subject of structural engineering. So all different things with expansion and impact and fire, even, what happens when there is a fire scenario, material problems, and what is going on in the material under all this kind of loading, dynamic loading, wind pressure, and yeah, so it's what is coming is quite demanding, and it will help if you motivate yourselves to really focus on what you are trying to achieve as a big picture. So these are, different types of loading, earthquakes here, and so on and so forth. And of course, the effect of moments and so on. So for now, I'm going to just move away from this and continue with the topics I'm trying to highlight today to you. So this is a kind of the different loadings applied on the system. And then we will proceed quickly to the application of the load. So that's also very important. Again, it's a very simple idea to look at how the load is applied. So the load can be applied as what we say concentrated force. Like if you look here, you have the wheel of the truck, and the contact area is very small compared to the size of the wheel and the size of the truck and the size of the bridge. And you can assume this force is concentrated or point load. Concentrated or point load. So this is the first type of load we will come across. And when you are dealing with this kind of problems, please remember, it does not really exist in reality, but this is just an approximation of this type of loading, concentrated load or point load. Again, in a very simple idea, as a revision quickly, we have what is called distributed load, or variable intensity. So this is a load which is not concentrated, not point load, but variable, like what you see here in the hydrostatic pressure behind the dam in front of you. So the pressure intensity, as you know from physics perhaps, or you can imagine as you go deeper in this water, the pressure will increase, and the pressure will increase in a linear manner according to the depth of the water. So this is a variable intensity loading starting with 0 and a maximum value here. And you will encounter this loading in many situations in engineering, including in geotechnical engineering and mechanics of materials, and even bending or soil mechanics. In different kind of situations, you will encounter this variation of the load, the variable intensity. It's basically like a pressure, if you like, a continuous variation, which you can think about it as the idea of the pressure from water. Yeah. Now, there is a very type of intensity which we use a lot in structural engineering. So that is a distributed load with constant intensity. Constant intensity, what we call uniformly distributed load, or we talk about it as an abbreviation, we say UDL. So as engineers in the office, we say, oh, what is the value of the UDL here? So the UDL is a constant intensity or uniform intensity distributed load over the length of the structure element. So if we present a beam like this, and if we think there is a constant intensity pressure, constant intensity loading on this beam, it could be actually the self-weight of this element, even the self-weight of this element. So how heavy this element is. If it's very big steel element, if you like, it could be similar to that actually. But anyway, so we can say the constant intensity on this element is 5 kilonewtons per meter length. So each meter, so that is 4 meters, each meter has got a weight of 5 kilonewtons, or has a pressure on it equivalent to 5 kilonewtons. And every half a meter is 2.5 kilonewtons, and so on and so forth. So this is, if you like, a constant intensity pressure acting on the beam, and you can think about it actually for now anyway as a self-weight. Maybe that will help you a bit, like this is how heavy this element is. You can think about that, or if you can think about like sandbags, resting supported on this beam, something like that. But it is basically a constant intensity pressure acting on this element, and the value of this constant intensity pressure, or the constant intensity loading, or the uniformly distributed load, can be established and can be calculated in real life examples. But in this module, in this course, we might give you this value, so make your life easy, but you need to appreciate what it is. So if you think about this constant intensity load, the UDL, the uniformly distributed load, acting on this element, which could be a self-weight, could be whatever, but it's constant intensity. So the resultant of this loading will be the value of the intensity, the value of the UDL, multiplied by the length on which it is acting. And have a look, please. It is 5 kilonewton per meter. You multiply it by 4 meter, and the resultant will be, of course, 20 kilonewton meters. So the resultant is not the actual loading. Remember this. This is a mistake some students make in the UK anyway. So they take away the intensity of the loading, the UDL, and they just replace it with the resultant. This is okay in some situations, and I will explain later what I'm saying. But you have to remember this is how it is. It is a constant intensity, uniformly distributed load, uniform pressure on the element. And this is a sketch I did in front of the students a long time ago to just explain the idea a little bit more. And if you can think about it as this slab, we call this slab resting on a beam, and the pressure from the slab on the beam. In this case, if the load is going just two directions like this, so the pressure is uniformly distributed pressure. And you can look at many examples in the textbooks, and this is another kind of image for you. So the pressure from the slab, if it is going to in one direction, like the example I sketched in front of the students, again, it will provide a constant intensity pressure on these what we call secondary beams. These beams here, where the load is going, so there will be uniformly distributed loads on these elements. And in this course, we are going to look at the effect of this loading on the grains of the material. What kind of issues related to what's happening inside the material as this load is transferred to the elements. And another image for you here to think about for the future. How the load is transferred. And here you can see, this is what I'm talking about, is a uniformly distributed load, UDL, transferred between the slab and the beams. Okay, so this is an idea which we need to keep in mind for the future. So let's now think about how these elements are supported. So that's very important to identify support reactions, so structural supports. So if a support prevents translation, linear movement, prevented in a given direction, the force, the reaction force is developed on the body in that direction. So if you stop translation, you will develop a linear reaction force. Okay, so there are many supports, but I like to speak very simplistically, very simple idea about ties or hangers. And you are stopping movement along the axis here at this point. So you will develop a reaction along the axis of this element. And of course, the element itself will be subjected to tension. But that's, that's an idea which is simple. Of course, we have to focus more on what's happening here in the future, but for now, you don't allow any movement in this direction. So you develop a reaction in this direction. You don't allow any linear translation, so you develop a linear force reaction. Same thing here. We call it a column or a strut, or even there is another word here which maybe I could add, post, P-O-S-T, but it doesn't matter really. At the end of the day, you have an element here, and it's loaded along the axis, and at this point, you don't allow movement along this axis. Of course, there are many other problems happening here, but I'm not talking about these problems. There is something called buckling and stability and all sorts of things. But for now, I'm just focusing on the idea there is no movement allowed. So you develop a reaction if you stop the movement in a certain direction. You see this quite a lot in bridges, and you can also think about it in buildings and different systems. So this is a ruler support. And here, you do not allow vertical movement. So you develop one vertical reaction. And it is free to move on this plane, so you don't allow any horizontal reaction. Of course, you would think, how about friction? Of course, there is some friction, but usually we ignore it in our analysis, in our initial analysis. So friction is ignored. We should think about the development of the reaction perpendicular to the movement of this ruler support. Sorry. I ended up moving the image, okay? So we have 1 degree of restraint in the vertical direction, and we can write it like that. So we can actually indicate it by these wheels here, which allow horizontal movement along this plane. So we develop a vertical reaction perpendicular to this plane. This reaction can be up or can be down, actually. So please understand, it looks like strange, but the reaction also can be down. If we need the reaction to go down, we need to design the reaction to do just that. So this is how it looks in reality. And this is how we design the support. As you can see here, this is a bridge. So it moves this way. So there's only one vertical reaction. Okay. You might see it in books like this, which is okay as well. So some books can indicate it in many ways. So a ruler support, basically indicating one reaction perpendicular to the plane of the movement. Some books like to call it, or there's another type of support which you can call, as you can see it here, a bit different, but it's exactly the same idea as the ruler support. It's called rocker. It rocks, basically, rocks freely, but it develops the same thing, one vertical reaction on the plane where you allow this idea of rocking. It cannot develop horizontal reaction. There is some friction, but we ignore the friction, and you only have one reaction on this perpendicular to the plane where the rocker is allowed to rock, if you like. So the other type of support is this one here, hinge or pin support. And I think you all know about these things. We're just trying to make sure because I realized maybe we need to clarify these things before we can move on. So a hinge support or pin, you can use either words, hinge or a pin. And it is basically a connection or a support which allows rotation. So it can rotate freely, like the ruler as well, actually, and the rocker. They rotate freely, but they stop vertical movement and horizontal movement. So they develop two components of the reaction, a vertical component and a horizontal component. So there's a vertical reaction and a horizontal reaction at a ruler support. So you will see this image. Sorry, what did I say? At a hinge support. I mean at a hinge support. I think I'm getting a bit tired. So you have two reactions developing. Two reactions are developed at a hinge support. And please note, both roller support and hinge supports, they allow rotations. So rotations are free at a roller support and at a hinge support. So this is the idea of the pin support. And you develop two reactions, as I mentioned. Force, reaction force in the y direction, in the x direction and the y direction. And for your information, this is also how this pin support can be constructed, which gives you some practical idea about what is going on. So you have this element here is inserted in this, perhaps, and there's a pin, like what you see here. So you have these leaves, if you like, and then you have the pin, and you have the member here, and of course the pin again is assumed to have no friction, frictionless, and then you have the idea of a pin or the idea of a hinge support. Okay, my friends, so that is really the third type of support which you are really required to be very clear about and to understand very clearly. So this support is called a fixed support or built-in support. So now we come to the idea of not allowing rotation. Rotation is not allowed, is prevented. So if rotation is prevented, there is a moment reaction exerted on this body. So if I fix this body or this element in the wall, very strongly fixed, the wall will actually exert a moment reaction here, a moment resistance. So the force here will try to rotate this element, and the wall will resist in the opposite direction. But the wall also will provide a vertical reaction and a horizontal reaction and a moment reaction. So at a fixed end, and we can indicate this kind of support situation like this. So the element itself, we can indicate it by a line like this, kind of representing this element, the center line of the element. You have external loadings, whatever the external loadings might be, point load, UDL, variable intensity, it does not matter. This is a fixed support condition, fixed. So you have three components of the reaction. I will give you a break soon, but for now, let's just finish this bit, and then you have some examples and you carry out some calculations. So you have a vertical component, horizontal component, vertical component, and moment rotational resistance, moment reaction. So please, before you solve any problem, if you have a fixed support, you must indicate three components of the reaction. So MA is a moment reaction, which is a reaction from the fixed end on the element, reaction from the fixed end on the element. So the resistance, if you like, from the fixed end on the element. So the element is trying to rotate, in this case, in the clockwise direction, and the fixing element, the fixing support or the fixed support is providing reaction to make sure there is no rotation at the fixed end. So rotation here is prevented, otherwise this element will collapse. In our course, we are going to assume the fixed end will provide total rotational restraint. There is no rotational whatsoever, rotation is zero. So here in our analysis, we are going to assume this is the case. In reality, there might be some rotation, which is a bit complicated for now, but we'll just leave it as that. So at a fixed end, no rotation, zero rotation is allowed. Okay. So in your analysis, if you want to analyze a fixed end, you can indicate three reactions as I've just mentioned on the element. So this is what's happening here. You will see this in textbooks. So this is what is going on. Another example of a fixed end. And if this element is loaded horizontally like this, and there is an effect to try to overturn it or rotate it in this direction, of course here these bolts will provide resistance. And maybe this sentence is a bit difficult for you to appreciate now, but the moment reaction is actually a couple, one force going down and one force going up, and distance between them. But maybe it's a bit difficult for you. If the force is acting this way, this will be up and this will be down, and you have a couple reaction, or the moment reaction will be actually a couple developing as a support point, one tension and one compression in the bolts acting in opposite directions. But anyway, that's not really hugely important now, but maybe you can imagine. Same thing here, taken from a building. So these connections here are connections where you have a fixed end, the steel and the concrete wall is providing total fixation of the element and resisting any rotational effects. Okay, my friends, I think we'll leave it as that, because these are the important supports. There are other types of supports, but we can discuss more after we take a break. I will make a coffee because I'm getting tired. So, I'll see you in 10 minutes, please. So I'll see you back at 6 past 11, if that's okay. Thank you very much. Thank you. So, welcome back. So, we'll proceed a little bit. I've got my coffee now, so a bit more awake. So, okay. So we'll proceed, please. So so now we are going to think about how to calculate support reactions. And I think the idea is very simple, really. And I will give you more kind of examples to be able to confidently calculate reactions. Because in many of the problems we are going to solve in the examination and when you work as an engineer, it's about really calculating reactions, calculating internal forces, calculating stresses, and so on. And calculating reactions is the first step in the solution. So if you are not confident in calculating reactions, the most of the solution might be inaccurate, might not be correct. So we're going to use this idea for equilibrium, static equilibrium. So equations of static equilibrium in two dimensions is what we discussed earlier, the conditions, the three conditions. The sum of the forces in the x direction, we choose two directions, x and y, orthogonal directions. Some of the components in the x must be equal to 0, and by looking as well. So we need to apply the calculations, but we need to look and examine all the time. We need to be aware of the calculations. And, equilibrium in all directions, actually. But yeah, we think about x and y in a linear manner, but also rotationally about any point. So these are the three conditions of equilibrium. Because we have three equations, we can only calculate three unknown reactions. Because mathematically, if you have three equations, you can only calculate three unknowns. Later on, we will teach you ways to solve problems when you have more than three reactions. But for now, this is a condition now for you at this level. So I've already mentioned this in a simple idea. The sum of the components in the x direction must be equal to 0. The sum of the components in the y direction must be equal to 0. And rotational equilibrium, which is the sum of moments. And I like this idea because it's a simple idea and it will help you a lot. So you can use textbook ideas by, pluses and minuses, and that's wonderful. It's no problem. But for me, I like to think about it in a simple way, And you can apply combination of, pluses and minuses, or this idea, very simple idea. The rotational equilibrium is the sum of moments, the sum of the rotational effects about any point, yes, any point in the plane. For equilibrium, this must be equal to 0. So, okay. So I say, all right, let's take sum of moments about any point in the clockwise direction must be equal to sum of moments about the same point in the anti-clockwise direction or the counterclockwise direction. And I can write it simplistically in a simple way like this. Very simple, huh? Sum of moments going in the clockwise direction must be equal to the sum of moments going in the counterclockwise direction, or the other way around. You can write this on this side or this on this side, it doesn't matter. But you want to balance the rotational effects about any point in the plane of the force system, which is in equilibrium. When you have equilibrium, you cannot have any rotational effects. Otherwise, the entire plane will be rotating forever. Okay? So when I apply the equations of equilibrium, assume that the body will remain rigid and not deform. So the geometry is not changing. This is a bit difficult to explain at our level now, but the geometry of the body at the moment is not changing. The geometry of the system is not changing. This is a statement here. But you don't need to be concerned too much about this statement for now, except that the geometry will stay the same. Perhaps we can do this example even if we do it again, just in case someone didn't do it before. So let's do this quickly, please. So we have this system here. And now what I'd like you to do is to think about, this is a rigid body or solid rigid body or whatever, could be anything really. Very soon, maybe next week, we will analyze something like that. and you have 10 kilonewtons acting horizontally, 10 kilonewtons acting vertically, and you have a ruler support here and a pin support here. These circles here, I will explain them next week, so you don't need to worry about this for now. You can just think about this as a solid body, a rigid body of any shape, it doesn't matter. And you have these forces acting on it, and this is how it is supported here. And I'd like you to calculate the reactions at F and D, please. I'll give you 5 minutes to do it. I think you have done it before, but let's do it again to be absolutely sure everyone is confident, if that's okay. 5 minutes? What are the reactions at F and D? And I will wait for your contribution in the chat box. And as I said, I will copy all the chat box in my record at the end of the session. Please note, all of you, you must really attempt this example and give me the answers, correct answers, because as I said, very soon we will move on to much harder topics. And if you have any issues related to calculating reactions, it will be hard for you later on. So I will encourage you all to solve all the problems I'm giving you, because I know what is happening in the future, what is coming. Excellent. I'm getting some answers here in the chat box. Wonderful. I will keep a record of that. Good. But as I said, please, all of you must be encouraged to find the solution. But I've got many of you actually giving me answers, so that's great. I will wait a couple of more minutes for other students to give me the answers. Good. Okay. Wonderful. So many of you got the correct answer, which is great. But if you haven't, please make sure you do it and you are confident in doing so. For me, also, I like to look. So I like to do things by looking. But I will go through what I've written in front of the students a long time ago. So I here wrote it as F1 and F2 and F3, but you can call it whatever you like. So the solution, I'm sorry if it's not very clear, it was handwritten in front of the students a long time ago, as I said, but very simple. You need to balance the system horizontally, which will give you straight away F3 must be equal to 10. Okay? And it will be pointing in the direction indicated. And you must balance the system vertically. So of course, that will give you straight away F1 plus F2 must be equal to 10. Yes, okay, some other solutions coming through, that's wonderful. And again, the idea of me applying the rotational equilibrium in a simple way. So the sum of the moment about any point must add up to 0. So rotation about point A, total rotational effect, total moment about A, and the clockwise direction must be equal to 0, must be equal to total rotational effect around A in the counterclockwise direction. So here is A, clockwise is 10 times 2, 10 times 2, and counterclockwise direction is going to be the 10 times 2 plus F1 times 4. So F1 will be 0, and F2 will be 10. And you can check, you can carry out check, really. You must all the time carry out check. So you can check moments about E, rotational effect about E, rotational effect about any point must be equal to 0. So this is the detailed calculations, and many of you did it correctly. That's wonderful. So let me show you something else which you can do by looking. So let's look at it together. So I'm looking. I'm sorry, I call the points differently in my solution, but it's okay. I'm sorry. It was a different kind of question I gave to the students at that time. So, but anyway, for here, we have these kind of points. So point F here, have a look what's happening around point F. Point F rotationally around point F is 10 times 2 in the counterclockwise direction from this 10. And what's happening around point F from this 10 is also 10 times 2 in the clockwise direction. So if you consider rotational effect around point F, you have this force and this force are balancing each other. So the vertical reaction from here must be equal to 0. So VD or reaction at D in the y direction, VD must be equal to 0. Otherwise, you don't have balance of moments around point F because it's already balanced rotationally by these two forces. So it is impossible to have any vertical reaction here. So you need to also think as well as calculating using the mathematical kind of formulation. So if you have any vertical force here, rotational effect, at least at point F, will not be achieved. Of course, at point F, you have possibility of two reactions. And if you don't have any vertical reaction here, any horizontal reaction here, it's obvious the vertical reaction at F will be equal to 10. And obvious the horizontal reaction will be equal to 10. So actually, this problem you can solve even by looking at it. As I said, because of the equilibrium rotationally around F is already achieved by the 10 horizontal and the 10 vertical. But anyway, so you can adopt this idea of checking all the time in your mind. Maybe we can try this one for now. So this is another problem. So now what we have here, a rocker support here, which I explained before. You can treat it as a roller support and a hinge support here. Or a pin. So here you'll have just one reaction, and here you have vertical and horizontal reaction. So calculate, please, the reactions and ignore the self weight. So ignore the weight of the beam itself. It can actually be quite heavy compared to these kind of forces, to be honest with you. But it's okay. For now, we're just saying ignore the weight for simplicity. Again, 5 minutes for you. I'll wait for you. So I'm waiting for you to give me the reactions at support A and support B for all these forces indicated on the beam. Great, wonderful. I'm getting some solutions here, some answers. That's wonderful. Thank you very much. Let's have a look. Anybody else? I will wait a few minutes to get more answers. What we have from Bao and from Min, we have the pin and the ruler reactions. which is great. So just a couple of more minutes for more colleagues to give solutions. So this is kind of almost like the minimum level you need to be confident with the same procedure, the same idea for equilibrium and support reactions. We need to understand them and be able to calculate the reactions. Yeah, I'll wait for you a couple of more minutes. Wonderful. We have more colleagues providing solutions. Great, great. Wonderful. Thank you. Wonderful. Thank you very much. Yeah, good. Okay. So let's check together, please, the solutions. So first, you need to establish what is called a free body diagram, which I don't know if you've heard this term before. If you haven't, we are going to talk about it. But I think for you is what I've just taught you is sufficient. But basically, the 600 newtons, as you have done in your solutions, is presented by its components of the 600 newtons, not kilonewtons, and the distance 0.2. Maybe you notice this as well. So this is the distance to the location of the pins. Yeah, more solutions coming through in the chat box. Wonderful, great, love it. So for equilibrium, you must achieve horizontal equilibrium, which means basically the sum of forces in the x direction. You see here, to work neatly, you can indicate the positive directions before you carry out the calculation, like what you can see here. If you want to do it this way, with pluses and minuses, is okay. So here, this is a positive direction in the x. Sigma forces in the x direction are equal to 0. So what do you have here? You have, of course, the free body diagram, or you put your reactions first. There's only one reaction here at A, and there are two reactions at B. So that is your decision. If you get this wrong, the solution will be wrong, I'm afraid. So 600 cosine 45 newtons going in the positive direction of x, which is assumed this direction. and in the negative direction is the reaction in the x at b, bx. So bx straight away is equal to 424, and when it comes out as positive, it means it's in the same direction as you assumed here. So please understand that. So if you want to be very clear, you can also indicate it is going in this direction here to make sure whoever is looking at your solution understands where exactly this force is going. But otherwise, the plus here means it's going in the same direction as the direction you assumed in the sketch. So most of you got all of this correct. And now let's have a look at the vertical equilibrium. The vertical equilibrium can be obtained from the vertical reactions. The reaction at AY, can be obtained by different ways. Many ways you can obtain it. The easiest way can be what is in front of you here. So taking moment, or this is what it says here, a direct solution for AY, for the vertical reaction Y, can be obtained by applying the moment equation or the rotational equilibrium around point B. Sigma moment around B is equal to 0. So let's see what is going on around point B. So here is B for you if you are not confident. If you are confident, it's okay. So at B, you have 200 here going through it, and Bx going through it, and By is going through it. All these forces do not have any rotational effect around B, so you can ignore all of them now because the arm of the moment around B is 0. So you can ignore all these three forces when you carry out this moment balance around B. So let's see what remains. What remains is the following. The 100 here times 2 around B. 100 Newton times 2 meter around B. Okay, wonderful. Going in the assumed positive direction. In this case, the textbook assumes this direction is positive. It's okay. It doesn't matter really. But you have to make indication of which direction you are assuming positive. And then what you have in the positive direction as well is this force here going in the same positive direction, which 600 sine 45 times 5. 5 because this distance here is 5. Okay. Now, I don't know if you've taken this into consideration, but you have also this force here makes a distance of 0.2 around point B. So this is the arm of the force here, AY, now will be affected by the rotational effect of this force around B. So 600 cosine 45 times the arm of the moment is 0.2, causing rotation in this direction, which is a negative direction according to our assumption here. And plus or minus now, so this is minus from here, and AY is also minus because going in this direction around B, AY times the total distance, which is 7. And this calculation here will give you AY as 319. So I can see some of you made a mistake in this. So please correct your mistake now. Yeah, so this is a good lesson. Someone saying, "Oh no." Okay, don't worry. This is why I gave you this question here. So please correct your mistake because all these forces here will have these two forces here will have a rotational effect around this point. So please make a note of this mistake. Do you have any question, please, about this mistake? Anyone? Okay. So, and if you then want to find by, again, will be a little bit different from your calculation because of the mistake in the ay. So the by, or the vertical reaction at B, will be basically the sum of the forces in the y direction will be equal to 0. So if you take upward as positive, so you have 319 going up, minus 600 sine 45, minus 100, minus 200, don't forget the 200, plus by, you have by coming out as positive 404. Sorry, 405. So that is really the solution of this little problem. So if you have made a mistake, please make a note of the mistake. Any questions, please? No? Oh, wonderful. Thank you very much indeed. So there was a small little problem here because we didn't notice the distance between this horizontal force and the point where the reactions are developing here. So this mistake was actually now appreciated, and in the future you will make sure you are focused on where the forces are applied and which point you are actually considering the rotational effect at. And as you've seen, this influences the value of AY and of course influence the value of BY. And in the future, we are going to calculate what's happening inside the material. And of course, if this is not right and this is not right, the values of the stresses inside the material. This is what the whole course is all about, the values of these stresses, which might lead to the collapse of the system or the yielding of this beam or whatever. So the values will not be correct. So please appreciate the importance of what we have just done. It's now 11:47, so I think we will just continue a little bit to investigate this a little bit more for your benefit. So so yeah, this is something for you to understand. You have to check your solution by now exploring the moment equilibrium or rotational equilibrium around point A. And maybe you can do this as a homework. So having established AY from the rotational equilibrium around B, and having established by the vertical equilibrium now, and having established the bx from the horizontal equilibrium, now we can just carry a check on the system by saying, all right, is the rotational equilibrium achieved around location A? And we can carry this out, and we can check our solution. Always develop a technique of checking your work. In engineering, we have to check because sometimes we make mistakes. Everyone makes mistakes. So you have to say, all right, I've done this now. Is equilibrium achieved rotationally around this point? In fact, it should be achieved around any point, this point as well. Any point in the plane of this force system, you must have zero moments, zero rotational effect. So now we run out of time, I'm afraid. So can I ask you any questions? have given you homework the last week before the TET holiday to calculate reactions for many systems, many beam systems. So this homework, I will ask you to submit it to us, please. You have it already in detail. So, and if you want me to remind you, I can remind you quickly before you go, if you don't mind. I've given you homework of these questions, I believe. Where? Here. So I've given you homework to calculate the reactions for all these systems, and we are going to analyze these systems in detail in your course, Mechanics of Materials. So if you attended the session just before the holidays, you have all these problems which I asked you to calculate the reactions for and submit your solutions to us perhaps before the session next week. If anyone doesn't have these problems, please shout, and I will give you chance to take a screenshot or a snip of any of these problems. Otherwise, I will say goodbye to you, and I will wish you a wonderful afternoon, evening, weekend. So you have a record of all these problems. At least take a snip or a screenshot of this problem minimum, and please calculate the reactions for this kind of problems as a starting point anyway. Will make life more complicated for you, I'm sorry to tell you. But as a starting point, please take a snip and submit your solutions to us before you come to next week. Any question, please? No questions? So now it's 11:50. So I will just now say goodbye to you, and I wish you all the best. I wish you a good remainder of your day and a good weekend. Thank you very much for your contribution. Before I leave, I must copy the chat box to have a record, but I'll let you go and I'll stay to copy the chat box. So please give me some time before you or I will take some time before I exit, so I can take. Actually, I can copy it now. Control C. I've already done that. Not quite. Sorry. Just 1 second, please. Okay. Control C. So I have a copy of the chat box. Okay. Thank you very much and goodbye.
Okay. Thank you very much, sir.
Thank you. Cheers.
Have a nice day.
Thank you. Same to you. Thank you. Bye-bye.
Bye-bye.